Okay, in our previous video we talked about Gaussian elimination, and we completed the programming of forward elimination. In this video, we will discuss and implement back substitution, which will complete the Gauss elimination algorithm. This step is not as difficult as the first step. Here, we had to figure out what the equations were. But for back substitution, the text already gives us what the equations are. So I'm going to, but we're going to have to make some modifications here because I use slightly different notation. So I'm going to go ahead and copy these equations here. And we'll put them in our file and see what we can do with them. All right, so notice this was our previous elimination step. Now let me go ahead and paste this here. And we'll do the modifications we need. Now, the solution that we're seeking is x, and it depends on what he has here, b and a. Now, as I mentioned, I used a notation that's slightly different from what he uses. By the time we're finished with our matrix, my value of b, what he calls BII, is the same thing as what I call the n plus first column of A. So that's B, that's A, n plus 1 I. All right, so this is the notation that we are going to use. Also, in my notation, I didn't have these superscripts here. Okay, so we can make this modification. I also want to say it would be better to put this equation first because this is the first equation that you use. So I'm going to go ahead and take this equation, move it up top here. Okay. And let's do some more cleanup here. We'll erase that. And let me move this down. Well, why don't we grab all of that? Okay, we'll move the whole thing down. Okay. Actually, let's fix this up. And I'll write it again. So in my notation, in our notation, oops, something went wrong there. Okay. In our notation, the b n is going to go to the nth entry of the n plus 1 column, and bi is going to be the n plus first, the ith entry of the n plus first column. And we also have no superscripts I. So I'm just going to go ahead and erase them right now. Well, why don't I, to make this clear, I'll just say, I'll just make it modified. Okay, so in order to modify correctly, let me just copy this and move it down here. And in order to make it correct, I don't need these superscripts, so I'm going to go ahead and erase those. Okay, erase the superscripts. And instead of B, I'm going to have the n plus first column of A, so I'm going to go ahead and erase these. Oh, I don't know what that's doing over there. Okay, so this is going to be, if I remember right, this is going to be A n plus 1 n, and then this is going to be A n plus 1 I. Okay. Now here, since we have I equals n minus 1 to 1, This is actually a loop. So I can write this as a loop. And this goes from I equals n minus 1 all the way down to 1. And then we're going to be doing this. This is going to be xi equals, here this is going to be, this is correct, a n plus 1 I. This is over aii. And then we're going to subtract. Now this summation we can actually write as a inner product or a dot product. And in fact, if x is a column vector and this A signifies a row vector, this can be written as a matrix multiplication. So I'm going to write that this way. This is A. This is going to be in the ith row. And its entries I plus 1 up to n. Up to n. And that's going to be dotted with the entries of x from I plus 1 up to n. Okay. That's a little bit unclear. Maybe I should make it a little bit bigger. Let's try it again. Okay. What I'm going to have here is a ith row, entries I plus 1 up to n. And that's going to be matrix product times x entries I plus 1 up to n. Okay. And we'll have to make this a column vector. This will be a row vector. And when you do matrix multiplication, you can have row times column, and that will work just fine. Okay, let me clear up some of this other garbage here. There's nothing here, so take that out. And this is just a plain old minus sign. So, because I want to have this clean so that I know what's going on. All right, so that's what I'm going to do. All I have to do is add a handful of statements. This gives me my last x, and this gives me my other x's. All right, so let me pull this up and pull this down and open my Gauss program. And at this point, I have my correct reduced matrix, so we're fine with that. Now I know that I want my x to be a column vector. So I'm going to go ahead and define x as a column vector. Let me just start out x as all zeros. So I'm going to set x equals. Now the way to set a vector as all zeros is just the command zeros. And you can look that up also in the help file. If I look up here, zeros. Okay. And here it gives me some descriptions. Zeros of m1, m2 gives me a vector, a matrix of size m1 rows, m2 columns with all zeros. So in this case, I want a n by 1 vector of zeros. So I'm going to take zeros of n1. All right. Now let me go back to the first statement here. This tells me what xn is going to be. And I can just input that statement exactly. Okay, so my last n, x of n, is going to be equal to A, this capital A, n plus 1 n divided by A n n. Okay. All right, so now I'm going to have to do a loop. Okay. So here's we're going to loop to find other x's. So I can take 4I equals 1, and it doesn't start at 1, it starts at n minus 1. The increment between successive values is minus 1, and the first value is 1. Okay. All right, now I'm going to want, this is going to be a little hard, but no, I think I've got room here. Let me pull this down. I'm going to want an equation for x of I. Now here I put a subscript, but in Scilab you have to write it this way. X of I is going to be equal to A. Now remember, again, in Scilab my matrix is with a capital, so I have to use a capital A. Small a is not going to work. You have A n plus 1 I. I guess I want to put a parenthesis here to get the denominator. Then I'm going to subtract A. Now this is the ith row, and it's the entries from I plus 1 up to n. So I have I plus 1 colon n. And that's going to be times, and this is a matrix times, it's matrix vector times. And that's times x entries I plus 1 up to n. So let me go back here. And here this is times x I plus 1 up to n. Close my parenthesis and divide by AII. AII. Okay. And that's it. I just need an n to end the loop. And we want to see if we got the right answer. So I'm going to ask for it to show me what x is. All right. Now, if all goes well, we'll have our answer. Let's see what we got in the console. Okay. Here it says invalid index, line 17. Okay, so let's take a look and see what we've got here. All right, in this video we continue our discussion of the Gauss elimination method. And if you remember, we have already done the first part, which is forward elimination. So we're okay with this. Forward elimination is good. Now we want to do back substitution. We have already arranged the equations so that the very last equation has only one variable. The second to last equation has two variables. Third to last has three variables, and so on. And the strategy is to solve first the last equation for the last variable. Once you know the last variable, you can plug that into the second to last equation and find the second to last variable. Once you know the last two variables, you can plug that into the third to last equation and find the third to last variable, and so on. Now, if you work it out, you'll get some equations for the variables. He's already worked out the equations for us, so we're just going to use the equations that he comes up with. However, he used a slightly different notation from what we've been using in this presentation. So what I'm going to do is I'm going to grab his equations, which are right here, and modify them accordingly. All right, so let me grab these equations. And we'll copy, and we'll move here. All right, so we got down to here, and our summary was here for the elimination. Now let me go ahead and paste back substitution down here. So this is for back substitution. Let me make it blue. Okay. Now, as I mentioned, in our notation, this is slightly different. If you recall, I made B into the last column of the augmented matrix. That means that BI is no longer BI. BI is going to be replaced with, now the ith entry of the last column is AI n plus 1. All right, so everywhere we see a BI, we're going to replace it with AI n plus 1. The other thing that we're going to do is he uses these superscripts here because he defined A prime and A prime prime and A prime prime prime. And I avoided that by redefining or resetting A equal to A prime. So we can eliminate all superscripts. All right? So let me write our equations below. Okay? We're going to start with this equation. So we'll start with xn equal to, now again, he has bn here. That for us, that's a n plus 1. And then we divide it by a n n. Then after that, he has these equations here. Now what this actually means when we go from I equals n minus 1 down to 1, that's a loop. So I'm just going to write it this way because that's how we're going to do it in Scilab. So the loop goes from I equals n minus 1 all the way down to 1. Now in Scilab, the way you do that is you put 2 dots, the increment is minus 1, and the final value is 1. Okay. Now during the ith iteration of the loop, I'm going to get xi, and here he has bi. Now I know that bi for me is the same thing as a I n plus 1. Then I need to subtract this sum. Now what is this sum? This sum is the product of, well, let me write it out so it's a little bit more clear. This is going to be a I plus 1 times x I plus 1. The next one's going to be a I plus 2 times x I plus 2. Okay. All the way up to a I n x n. Right, so that's what this summation is. And we'll see there's a shorter way to do this in Scilab. And all of this is divided by AII. Okay. Now we're done. This will give us all of the x's. So this is we go to the next I. And then after that we're done. We should be able to display all the values of x and get the result. Let me explain a little bit better how we're going to do this. All right. We can consider this as a product of two vectors. All right, so let me do something here. I'm going to make this a little bit longer so I have room. Okay. All right, so let me go down here and explain what I plus 1 times xi plus 1 all the way up to a I n x n. I can write that this way. I can write it as this vector, a I plus 1 dot 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 up to a I n times x I plus 1 dot 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 xn. Okay? And this is an ordinary matrix product. This times this plus the second times the second, all the way down to the nth times the nth. Okay? So when I write this in Scilab, I'm going to use this form to write it very compactly. So this form is going to be equal to this expression here. Okay, so now we're ready to go over to Scilab and actually write this code. All right, so here we go to Scilab. I'm looking in my notes here. Now this is the part we've already done. We're fine with that. Hang on a second. I made a mistake. I did it beforehand, so I erased it. All right, so let's reconstruct this code. This is the code that gives us the elimination of variables. So now we want to go ahead and find our x's. All right. So the first part of that, xn is given by this equation. We can do that here. So here now we're going to do back substitution. My last value of, so this is my last value. Okay. So the equation here is x of n is equal to a of n plus 1 divided by a n. All right. Now there's something I want to do before starting on this computation. I want to tell Scilab that x is a column vector. Otherwise, Scilab may not know. So I'm going to go ahead here and press enter and define x initially as a column vector of zeros. So I'm going to initialize x as a column vector. I know it's these little sticky points that cause a lot of trouble. So here my x, I know my x is going to be a column vector with n rows and 1 column. And let me first fill it with zeros. All right, now how do you fill a vector with zeros? Let's go to the help and let's type in zeros. All right, and look, here it says zeros is matrix made of zeros. And this gives some examples. The best way to figure out what the statement does is go down to the bottom where it gives examples. All right, here he says zeros, and it's pretty clear that if I want a square matrix with a 3 by 3 matrix with zeros, I'm going to have zeros 3, 3. In my case, I want a column vector with n rows and 1 column. So I'm going to go back and I'm going to define x as zeros, n rows, 1 column. All right, so now I've told Scilab that x is a column vector. All right, so let me go back here and see what's next. All right, the next part is this loop from I goes to n minus 1 down to 1. And I can type that in exactly as I have it up there. Okay, and so here's the remaining values of x. So here I'm going to have 4I equals n minus 1 colon minus 1 colon 1. Now, in the ith iteration of the loop, I'm going to want to get xi, which is indicated right here. So let me push that up a little bit. I'm going to want to put this equation now into my Scilab. So this is x of I equals, now I've got a big fraction in the numerator, so I better put a parenthesis. Then here I have I have ai n plus 1. Now notice I'm using capital A here. That's important because my matrix was defined as capital A. Now I'm going to subtract, And as I mentioned, I'm going to write this as a matrix product, which is good because Scilab does matrix products automatically. So let's see how this matrix product works. It's going to be this vector, the ith row of A from column I plus 1 to n, times x, this part of the column vector of x. Right? So the way that works is that's going to be A, ith row, I plus 1 up to n, times x, and then x we're just going to take the I plus 1 up to n, and that's in the first column, so we can do it that way. The denominator on this expression is aii, so I have to go down here and type in aii for the denominator. All right, and that was the only statement in my loop. So I'll go ahead and type end. And let's see our result. I'll see if we get x correctly. And we have our code, our beautiful little code, only 24 lines, half of them are comments. And this should do Gaussian elimination for us. Just think of all the hours you spent doing Gaussian elimination by hand. Okay, so let's see if we can make this work. We run the code, and we'll go to the console. And lo and behold, it gives us this vector. And if we take this vector and multiply it by the original A, we can see if we get our value of B. Okay, the original A was over here. So I'm going to copy this here. And I'm going to take it to the console window. And let me paste it here. And then we'll do times x. Okay. We get 204, which just happened to be the initial vector b. So we have succeeded. Go out and buy yourself a champagne.